SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are now in the module 5 of applied thermodynamics course, and title of this module is refrigeration and air conditioning systems. So, till this point of time, whatever topics we have discussed in this course, they were treated as power producing devices. Now, this is a sector which is refrigeration and air conditioning system, where the devices are called as power consuming devices. So, this is again based on the fundamental thermodynamic cycle, that is Carnot cycle, and when this Carnot cycle is operated in a reverse mode, there we can say the heat can be transferred from low temperature region to the high temperature region if a necessary amount of work is being supplied. So, based on this, the refrigeration and air conditioning systems are evolved. Now, under this particular module, we will talk about the following 6 topics. First 2 lectures will be devoted mainly on vapor compression refrigerating system. So, this is part 1 and part 2. Then we will move back to the vapor absorption refrigeration, and we will give some introduction to the refrigerants. Then we will move to air conditioning aspects. Now, in the air conditioning aspects, the first fundamental things that we are going to study is the principle of psychromatics, where it deals with the properties of moist air, and we will discuss about some fundamental air conditioning processes, and finally, in the last lecture we will be mainly focusing on a particular application oriented topic, that is cooling towers and air washers. And with this philosophy, we can say how a continuous year wise air conditioning requirements can be achieved through these air washers. So, let us start the first topic or first lecture, and this is that is the vapor compression refrigeration systems. Now, on this vapor compression refrigeration system, first we will give some brief introductions, then we will talk about how this vapor compression refrigeration was evolved. So, it starts with the Carnot refrigeration cycle with certain limitations and drawbacks in the Carnot cycle. The realistic version of the refrigeration system was evolved, and we call this as a vapor compression system. The next we will talk about the vapor compression cycle. So, let me start the vapor refrigeration systems. So, just to give some introductory remarks, we can say that the purpose of a refrigeration system is to maintain cold region at a temperature below the surroundings. And in fact, we in our day to day life, we all have refrigerators and air conditioning units in our house, and these refrigerating systems, they require the electric power as inputs, that is the fundamental source in which is required for them. And at the cost of that, what we are going to get is a desired effect, and in our case, this desired effect is some kind of coldness or cold region where the body has to be maintained. So, the performance of a power driven refrigeration system is defined as the ratio of desired effect to the power consumed by the systems. So, here the desired effect could be there are two situations that one can have a refrigeration cycle or a heat pump cycles. So, if you look at this particular figure, here the entire idea, and in fact this particular figure is mainly derived from the Carnot cycle, which says that we have a cyclic device, and in our case it is either a refrigerator or a heat pump, and which consumes work as a input, and by consuming this work as input, the cyclic device is able to transfer heat from the cold reservoir, and it can reject this heat to the hot reservoir. So, based on that we say that cold reservoir has from the cold reservoir, which is maintained at certain low temperatures, it takes QC amount of heat and it rejects heat to the hot reservoir, it QH, and based on which we can say the amount of net work which is fed as input, and we call as a cyclic work. Now, here there are two aspects. One is this device, cyclic device, can act as a refrigeration cycle or it can act as a heat pump cycle, and this depends on the what is the desired effect which is required by the user. So, if our desired effect is a hot reservoir, that means our main requirement is that for example, if you have a house which requires some kind of heat as input and you need to supply heat into that house or apartment, then that becomes a heat pump cycle, because that is our desired effect, and based on the work input would be W cycle. And this and when you say this, the cold reservoir could be ambient conditions. The other extreme situation could be what we are using in our day to day life, that if we have a refrigerator where a space needs to be reserved for as a cold compartment, then continuously some amount of heat must be extracted from that compartment, and finally it has to be rejected to the atmosphere. So, in other side of the story is that your desired effect is the compartment which is in which we need to maintain the low temperatures. So, in that case your requirement of main requirement is to heat extraction from the compartment. So, if you say that our desired effect is QC, then we call this as a refrigeration cycle. So, a refrigeration cycle maintains the temperature below the surroundings, whereas heat pump cycle provides the temperature above the surroundings. But both the cycles, they require some work input that needs to be supplied for executing the cycle. And the common applications in our day to day life is food preservation, air conditioning units, they fall under refrigeration cycle. Heat transfer process in the industrial cycle require higher elevated temperature from the surroundings. So, they require some kind of heat pump cycle. Both air conditioning and refrigeration systems can be modeled, and these modeling can be done by three means. First thing is that the vapor compression systems. So, in a vapor compression systems, main thermodynamic essential requirement is that in order to get the desired effect or coldness, we require the high grade energy as work input. So, this work may be treated as and in this case it is a electrical work. So, that is the first essential requirement for a vapor compression systems. And of course, the efficiency, since your high grade energy is work, so efficiency of this systems is higher. And when you talk about a vapor absorption systems, there are some situations which we can use the waste heat as one of the requirement of heat source. So, we call this as it uses the major source of energy that comes as a heat source. It could be a solar energy, it could be a waste heat, or it can be a very basic thing is that it is as a low grade energy resources. But however, there could be some minimal amount of high grade energy in the form of work, but that is not taken into account here, because major contribution comes from the low grade energy. So, this is another aspect, we call this as a vapor absorption refrigeration systems. And third category, we normally call it as a gas cycle refrigerations, and mostly they are used in the aircraft refrigeration systems. And in fact, this is something similar to a gas turbine cycle which we have covered, and this gas turbine cycle is mainly governed through the air standard cycle known as Brayton cycle. Now, if you use this Brayton cycle in a reverse mode, then we call this as a reverse Brayton cycle, and simply we call as air cycle refrigerations. This is the another fundamental segment where which is mostly used in the case of gas turbine engines, when the Brayton cycle is operated in a reverse mode. Now, let me start the first basic thermodynamic aspects, that is Carnot refrigeration cycles. We all know from the basic thermodynamics we have a Carnot cycle, and this Carnot cycle is a we call this as a hypothetical or theoretical cycle which is never achieved in this practice, but however, there are many realistic version of this Carnot cycles. From this Carnot cycles other cycles were evolved, like steam power plant, the Rankine cycle was evolved. In a IC engines, from the Carnot cycle we can evolve Otto cycles, diesel cycle, and so many things, and in a gas turbine engines Brayton cycle was derived. And similarly here also in a refrigeration cycle, although the first thing is that when you talk about refrigeration cycle, we have to think about a reversed Carnot cycle, then only we can find a realistic version of the refrigeration cycle. So, first thing is that when you look at a Carnot cycle, it has there are some hypothetical devices, what we call as a turbine, boiler, pump, condenser. They are put in a circuit, in a thermal circuit manner, and in one case it's a cyclic device, and finally we get a work output from the turbine, and in this process this cyclic device takes heat from the hot reservoir and rejects heat to the cold reservoir, and our main intention is the work output. Now, if you think about this particular Carnot cycle in a reverse mode, so where heat is taken from the cold reservoir and it is rejected to hot reservoir, and in this process the work that is getting given as input is mainly given as a work input WC, and it is given to the compressors, and here this entire things we call this as a cyclic device, and this particular things we call this as a reversed Carnot cycle. And many a times we also call this as a Carnot refrigeration cycle. Instead of using word reverse, we can also say Carnot refrigeration cycle. So, in a reverse Carnot cycle or Carnot refrigeration cycle is executed by a refrigerant circulating steadily through series of components connected in series, and all the process, and here the components are turbine, condenser, compressor, and evaporator. All the processes are internally reversible. There is no irreversibility due to the heat transfer between the refrigerant and the region that occur with a negligible temperature difference. And typical diagram is a rectangle. In a TS diagram, the cyclic processes are represented as a rectangle in a TS diagrams, whereas in the PV diagrams this cyclic processes has two reversible isothermal processes and two reversible adiabatic processes. The process starts from 1 to 2, which is in a compressor. So, we say isentropic compression, and then 2 to 3 constant temperature heat rejection, and 3 to 4 is a turbine process, it is again isentropic process. 4 to 1 is also isothermal process, in which heat is given as input from this space to be cooled, and again the cycle starts with 1, 2, 3, 4. So, here the processes are given as 1, 2, 3, 4 in the PV diagrams. So, the very basic philosophy that there are two temperatures, that is warm region temperature, which is defined as TH, and cold region temperature TC. So, these two are fixed temperature on which the cycle operates. So, here what happens, refrigerant enters from a evaporator as a two phase liquid vapor mixture from the state 4, where there is a change in the phase from liquid to vapor as a result of heat transfer from the region at temperature Tc to the refrigerant, and both temperature and pressure remains constant in the process 4 to 1. The refrigerant is then compressed adiabatically from 1 to 2, for which the temperature refrigerant increases from Tc to Th. Of course, since the temperature increases, pressure also gets increased. Then refrigerant passes through a condenser, where it changes again its phase from the saturated vapor to the liquid as a result of heat transfer in the region at the region Th. That means, a constant temperature region heat transfer in the condenser, and this process is denoted as a 2-3 process 2-3, and where the temperature as well as pressure remains constant. Finally, the refrigerant return to the state inlet of evaporator by expanding adiabatically through a turbine. So, this process is taken from 3 to 4. So, in this process the temperature finally drops from Th to Tc. So, there is decrease in the pressure. So, what we can say is that entire cyclic device operate between two temperature Th and Tc, and it operates in a cyclic manner. And from this we can do some little bit of background of mathematical background by looking at the area under this Th diagram for the cycle 1, 2, 3, 4. So, our main intention is to find out, like in a conventional Carnot cycle we call this as efficiency, and in this case find the effectiveness of a Carnot refrigeration cycle, we call this as a coefficient of performance, and this coefficient of performance is defined for a reversed Carnot cycle. And to get this parameter, what we have to look into is that we have to recall this diagram 1, 2, 3, 4, and we have to see that how much heat gets added from the cold region to the refrigerant, which is in this case is nothing but the process, the refrigerant comes into picture when it is in the evaporator, in which heat is taken from the cold regions. So, this process is from 4 to 1. So, and when you take about how much heat is added, so you can say area 1 CB41, 1 CB41 is that area refers to the heat added from the cold regions, and heat rejected to the from the refrigerant to warm region will be, the process is 2, 3. So, you can say 2 CB4 3 2, and from this we can find out what is the net work done. Net work done is nothing but area 1, 2, 3, 4. Then we can calculate the maximum coefficient of performance, that is beta max, that is nothing but Q dot in, if you take per unit mass, Q dot in by Wc minus Wt. So, from this a simple mathematical area we can calculate, and finally we can say we can find a parameter which is beta max, and we call this as a maximum coefficient of performance, and this is nothing but the Carnot COP. Normally we call this as a Carnot COP. And here we call this as a Tc, beta max will be equal to Tc divided by Th minus Tc. Okay. Now, when you deal with Carnot cycle, we also found out that there are many limitations, because all realistic cycle which produces power, they cannot work on the mode the way the Carnot cycle imposes. Like for example, heat addition or heat rejection by maintaining constant temperature is highly impossible, although it is theoretically possible by assuming a very quasi-static processes or very slow processes, but that is not possible. So, for that reason, in a similar sense, we also find difficulties in running Carnot refrigeration cycles, and they are, we call this as their drawbacks. and because of their restrictions the actual vapors compression systems differs from the Carnot cycle, and for which the coefficient of performance is considerably lower. Now, what are the different drawbacks or important drawbacks? There are basically three drawbacks in which the actual system differs from the Carnot cycle. First is maintaining refrigerant temperature in the heat exchanger, or in particular in heat exchanger in our term we call this as a condenser or evaporator. We say the TH and TC are the temperature of heat sources that are maintained, but maintaining TH and TC it is difficult to extract heat or reject heat maintaining same temperatures. So, this is a one important drawbacks. Second drawbacks that comes in if you look at the compressor. Now, in a compressor whatever available compressors are there in the market, they normally use it because the word compressor is used when it is used in a gas phase or vapor phase. Now, if you look at our TS temperature entropy diagram, we can see that the compression process is mostly occurring in the wet region where the refrigerant is wet. So, but we require a dry compressions. So, there is a limitations that we have to move to wet from wet compression to we have to move to dry compressions. So, thereby the process in which the Carnot cycle says that we have to do it in isentropic compression, that is not possible. So, to avoid wet compression in the compressors, that is another limitations. Third limitation is expansion in the turbine. So, ideally our main intention in a refrigeration cycle to maintain the coldness, and we really do not work we do not intend to have a turbine to, because normally the word turbine is used when it is used as a power producing device, but here in our refrigeration cycle that is not the main intention, although that turbine power is getting utilized, but that requirement is very low as compared to work input for the system. So, your main work input that goes into the system is through the compressors. So, ideally putting a very big devices in the name of turbine does not make sense. So, the turbine is replaced with another device and we call this as a expansion valve. So, that is the reason the Carnot cycle departs or differs from a actual vapor compression cycles. So, it refers as a expansion valve. So, finally, we landed up by putting these limitations, the thermal circuit now becomes, the components now are called as evaporator, in which the heat is extracted from this region to be cooled, compressor where the only dry vapors gets compressed to a high pressure, and in the condenser heat is getting rejected, so it is a constant temperature heat rejection, and finally from this while from high temperature to low temperature or from high pressure to low pressure, both pressure and temperature can be regulated by a valve, or many times we call it a throttle valve, or people call it as expansion valve, or mainly maybe throttle valve is a right word as far as the refrigeration cycle is concerned, and we will say it is a expansion valve. So, in this way the components are now changed, and with this change in the component we call this as a vapor compression cycle or refrigeration cycle. So, now let us go deep into the what are the different drawbacks one by one. So, first drawback I put that Carnot cycle put that if you talk about the warm region temperature which is TH and cold region temperature which is TC, but the actual cycle in a when you run this, I mean when you use in the component, if you talk about evaporator, the evaporator temperature would be much less than this cold region temperatures, then only it is able to take out heat from the cold region. And similarly, when you take the high temperature side, the condenser has to operate much above, so that the refrigerant can reject it to the warm region temperature. Heat rejection is possible. So, TH, if you look at this particular figure, your actual condenser temperature, that is T dash H, is higher than the TH, and the evaporator temperature T dash C is lower than the cold region temperatures. So, this put a restriction, and because of this region, if you actually calculate the beta or coefficient of performance of a actual vapor compression cycle, it now becomes T C dash by T H dash minus T C dash, and obviously beta max is T C by T H minus T C. So, by looking at this diagram, we can clearly say that actual COP will be always less than the maximum COP of the cycle or Carnot COP. Okay. And next point that I have also mentioned, that dry versus wet compressions. If you look at this particular figure, in the compressor, what does this happen, that after rejecting, after taking this heat, the refrigerant now enters in a vapor region, and when in the vapor region at state 1, it enters the compressor. But if you look at this particular figure, the compression and this particular compression mode 1 dash is still in the region of wet region, and we say that your compression gets terminated at point 2 dash, and that point only it is when it is only saturated vapor refrigerant is available at 2 dash, but this particular process is not allowed, because we say that 1 dash should lie on this saturation vapor curve somewhere at this point. Then only we have to say that the compressor can operate when the refrigerant is in dry mode, and that particular situation we call this as a dry compressions. So, here I have made a distinction what is a dry and wet compressions. The 1 dash 2 dash occurs in the liquid vapor mixture, commonly known as wet compression, and this particular thing should be avoided, because the presence of liquid droplets are harmful for the compressors. So, rather a dry compression is adopted for an actual cycle. And third thing is that this throttling process. So, as I mentioned that there is no requirement of a turbine. So, turbines is replaced with a expansion valve, and this particular valve we call this as a throttle valve, and this thermodynamic process for this throttle valve we call this as a throttling process. So, here the expansion process from refrigerant starting from saturated liquid at 3 dash to the liquid vapor mixture 4 dash is impractical, because it produces a relative small work output as compared to the compressor input. So, this work output from the turbine is normally sacrificed by replacing it with a throttle valve. And so, and this throttle valve is nothing, in this case is nothing but your expansion valve, and by taking all these modifications we call this cycle as a vapor compression refrigeration cycle. Now, we will move to that we come to know that the Carnot refrigeration cycle is no longer is possible in a realistic way. So, we have to rely on a vapor compression system or cycle, and the actual vapor compression, and there are two versions here when you talk about vapor compression system. One is ideal version, other is actual version. So, first thing is that we will have to, by replacing those components, let us see that how the diagram looks like in a TS plot. Now, if you look at these components now that is required, our essential requirement that at state 1 the refrigerant should be at least a saturated or superheated vapor, and at state 3 that the refrigerant state would be at the saturated minimum level should be saturated liquid state, and this process 3 to 4 is an expansion process, and we call this as a throttling process. So, on a TS diagram, the cyclic diagram that now, and of course, still we have retaining that assumption that compression process is still isentropic. So, if you look at the process starts with let us say 4, where the refrigerant takes the heat from the space to be cooled. Now, after taking the heat, it goes to becomes saturated vapor, where it enters into the compressors, and after getting compressed in the compressor, and this process is we call this as isentropic process, and final state becomes 2s. So, if you look at this TS diagram, and there are two pressure limits that operates, one is low pressure, other is high pressure. High pressure is nothing but remains at the constant that is at a condenser. Low pressure is in the evaporator. So, process 4.1 is in the evaporator, and process 2s and 3 is in the condenser. And on a TS diagrams, these are nothing but the constant pressure lines, which is represented here. So, from 4 to 1, the arrow direction shows that the refrigerant follows in this cyclic process. So, 1 2s is the isentropic compression, from 2s to 3, where heat is getting rejected from the refrigerant in the condenser, and finally from 3 to 4 it is a throttling process. And here one important thing that here the line 3 4 is given as a dotted line, because the throttling processes is always irreversible, whereas other processes we can ensure that the other processes can be considered as a reversible processes, except this throttling. Okay. So, evaporator, compressor, condenser, then throttle. So, in a TS diagram now we are able to show that how the cyclic process should look like in a ideal version of vapor compression system. So, that is the minimum requirement that we must have to run a refrigeration system, and we call this as a vapor compression systems, or many times we call as a vapor compression refrigeration cycle. So, the complete vapor compression refrigeration cycle now consists of series of internally reversible processes except throttling. One is isentropic compression of refrigerant in the to the condenser pressure, process 1 to s, heat transfer from the refrigerant at condenser pressure, that is process 2s to 3, change of state of refrigerant from liquid state to the liquid vapor mixture through a throttling process, that is 3 to 4, and finally heat transfer to the refrigerant at constant evaporator pressure to complete the cycle, that is 4.1. Okay. Now, after having said all these things, now let us find what is the how you need to quantify. So, basically when you talk about refrigeration load, we call this as a refrigeration capacity is one of the word that we frequently used. It is nothing but the how much heat is getting extracted from the cold regions. So, we must quantify from this temperature entropy diagram. So, if you look at these particular things, the refrigeration capacity, that means we are looking at a process 4.1 which occurs in the evaporator. Okay. From this if you look at, since they are cyclic devices, we can find out the amount that heat comes from the space is nothing but Q in, rate of heat transfer, and per unit mass flow of refrigerant, m dot is the mass flow of refrigerant, and that is nothing but enthalpy difference. This we can simply use the steady state energy equation, where Q dot is nothing but m dot into H1 minus H4. So, this is how we call this as a refrigerating load, and but in refrigeration term this particular load is called as a refrigeration capacity. So, as the refrigerant passes through the evaporator, the heat transfer from the refrigerated space results vaporization of refrigerant. Now, considering control volume enclosing the refrigerant in the evaporator, the rate of heat transfer per unit mass is known as refrigeration capacity. And in this our term, the refrigeration capacity normally referred as tons of refrigeration. In fact, in our commercially when you say that the capacity of AC or refrigerator or something, we say 1.5 ton, 2 ton, something like that. We call this as tons of refrigeration. So, what does this mean? 1 ton of refrigeration, or simply we call it as 1 TR, is equivalent to the production of cold at a rate in which heat is removed from 1 ton of water at 0 degree centigrade to ice at 0 degree centigrade in 24 hours. We take 1 ton of water and we want to remove heat from this water to make it ice. So, amount of heat that is required in 24 hours is nothing but 1 TR. So, simply if you calculate the latent heat of vaporization for ice and putting that value, 1 TR is now equivalent to this values, and in our SI term 1 TR is nothing but 3.5 kilowatt, and if you refer in or it is about 200 kilojoule per minute, or in calorie term it is 50 kilocalorie per minute. So, in our case we can simply use 1 TR is 3.52 kilowatt. Now, moving further, we are now going to compressor work and condenser load. This compressor process is 1 to 2S, which is isentropic compression, and condenser process is 2S to 3. So, it is compressor 1 2S and 2S to 3 it condenser. So, simply steady flow energy equations we can use apply. So, compressor work and per unit mass W dot C will be H2S minus H1, and condenser load can be calculated as Q dot out by M dot. So, here condenser means is Q out, compressor means W dot in, and here this can be calculated as W dot C by M or Q dot out by M dot. So, H2S minus H1 is the your compressor work, and H2 minus H3 is your condenser load. So, the compressor work is nothing but the refrigerant leaving from the evaporator is compressed to a relatively high pressure and temperature in the compressor. So, for a control volume enclosing the compressor, the power input requirement per unit mass flow of refrigerant is known as the compressor work. Similarly, condenser load, when the refrigerant passes through a condenser, the heat transfer occurs from the cooler refrigerant to the surroundings. So, considering the control volume enclosing the refrigerant in the condenser, the rate of heat rejection from the refrigerant per unit mass is known as the condenser load. Then next process is throttling. So, we went 4 to 1, 1 to 2S, 2S to 3. Now, this throttling process is from 3 to 4. Now, here this throttling process is a isoenthalpic process, it is a constant enthalpy process. So, in a constant enthalpy process means the H3 at state point 3 is equal to H4. So, the in a throttling process, the refrigerant at the exit of condenser expands to evaporator pressure through a throttle valve, and the process is known as a throttling process. Here the refrigerant pressure drops through a irreversible adiabatic expansion with increase in the specific entropy. See, that is the reason we say it is a not an isentropic process, because if you see there is an increase in the entropy, and the exit state is the two phase liquid vapor mixture. And from this we also know that we know the evaporator load from 4 to 1, compressor load 1 to 2s, condenser load 2s to 3. So, we now require what is Q dot in and what is Q dot out, and we also know what is W dot compressor work, which is input. So, from this we can calculate the coefficient of performance for this cycle, which is beta is equal to Q dot in by m dot divided by W dot C by m. So, we can now calculate H 1 minus H 4 divided by H 2 S minus H 1. So, this is how we define the COP of the refrigerant. Okay. So, with this I will come to the end of this particular lecture segments, and the end we will try to solve some numerical problems which has been covered in this lecture. So, the first problem is based on a refrigerator, but in this one thing I just need to emphasize, here the problems are very simple and it is more or less kind of algebraic calculations rather than using big expressions. So, in that sense this particular module, in fact this particular module is relatively easy module or easier module, and as far as the problems are concerned. So, let us start the first question. A refrigerator maintains a freezing compartment at minus 5 degrees centigrades when the surrounding temperature is 30 degrees centigrades. The rate of heat removal from the freezing compartment is 8000 kilojoule per hour, while power input to the compressor is 3000 kilojoule per hour. We have to determine the COP of the refrigerator, and here the heat removal as well as power input is given, that is one kind of COP that you can get. At the same time we also know the temperatures limits. So, from this we can find the maximum COP or Carnot COP for this cycle, and idea is that you have to compare and in what way these both the COPs are performing. So, to do that, first thing that you have to do is that you have to do this thermal circuit. So, we have a refrigerator, it takes some heat input W dot in, and this refrigerator takes heat from a freezing compartment. We say this is as a freezing compartment, and this compartment is maintained at low temperature, that is minus 5 degrees centigrade, and this minus 5 degrees centigrade is nothing but 268 Kelvin, whereas high temperature which is surroundings, so it is TH, that is maintained as 30 degree centigrade, and this is 303 Kelvin, and this refrigerator rejects heat. So, you can say QC is the heat taken from the freezing compartment, QH is the heat that is getting rejected. So, you have to put dot here because this is as a rate as given. So, what is given here? QC dot, that is from this freezing compartment, amount of it that is taken is 8000 kilojoule per hour, and what is the power input that is given to the compressor? W dot C 3000 kilojoule per hour. So, we can calculate beta COP, beta simply that is nothing but Q dot C by W dot in. So, it is 8000 divided by 3000. So, this is 2.67. Another way we can relook the COP based on the temperature. So, we call this as a beta max, and this is nothing but your Carnot COP, and this can be written as Tc by Th minus Tc, and by putting this number 268 divided by 303 minus 268, and this number is 7.65, and obviously beta less than beta max, and we say that actual. So, it is a kind of thing, that means where refrigerator is not performing up to the Carnot cycle limit. So, this is how we call this as a actual refrigerator, which for which the COP is close to 2.67, but its actual maximum COP could be as high as 7.65. And one interesting thing I understand today, COP value is always it could be higher than 1 or less than 1, whereas when you talk about efficiency, it is always less than 1. Now, another problem is based on heat pump cycle. So, here we have an apartment which requires 630 megajoule per day to maintain its temperature at 20 degrees centigrade, when the outside temperature is minus 2 degrees centigrade. It requires a electric heat pump to supply this energy. So, you have to calculate a minimum theoretical work input for 1 day operations, and if you take the cost of electricity as 1 rupees per kilowatt hour, what will be the minimum theoretical cost to operate the heat pump. Now, when you say minimum theoretical cost or minimum work input, then it must be a Carnot, because the Carnot heat pump or refrigeration system should require the minimum amount of work. So, considering that, we have to solve this particular problem. Then to solve this problem, first thing we have to draw this cycle. So, we have an apartment which requires heat to be delivered QH, and this is 630 megajoule per day, and this temperature is to be maintained at 20 degrees centigrade, that is 293 Kelvin, and this heat needs to be supplied by a heat pump which requires work input, and to do that it must take heat from surroundings. This surrounding is at minus 2 degrees centigrade, that is 271 Kelvin, and in this case it is QC, and this is not required here. And so, and here to find this COP, we have to represent this as a gamma. Just to make a notation, when I write gamma, it refers to the COP of a heat pump cycle, and that is nothing but QH by W, because your desired effect is QH, and gamma goes to gamma minimum, and when it is Carnot heat pump cycle. Sorry, gamma max. So, gamma max can now be calculated as Th, because desired effect is Th, divided Th by Tc, and from this we can put 293 by 293 minus 271. So, gamma max now 13.3, and when we have this gamma max, that point of things, we can now say your gamma must be 13.3, for which we have to minimum work input. So, now putting this as here, W minimum would be QH by gamma, that is QH is given 630 divided by 13.3, and this is 47.4 megajoule per day, and we can simply write this as a 47.4 into 10 to the power 3 kilojoule per day, that is required, because you are given with cost of electricity is 1 rupees per kilowatt hour. So, somehow you have to change this in the to the form kilojoule. Now, cost of electricity, we can find out how much kilowatt hour per day would be. So, W would be 47.3 into 10 to the power 3 into 1 by 3600. So, this turns out to be 13.15 kilowatt hour per day. So, that means we have converted to kilowatt hour. So, when you have converted, but we require cost of electricity. So, cost of electricity or minimum theoretical cost would be 1 rupees per kilowatt hour. We are consuming 13.15 kilowatt hour. So, minimum theoretical cost would be C is equal to 13.15 rupees per day. So, this is how we can calculate, and you can just multiply with 30. So, we can say monthly heat electricity billing for running this heat pump. Now, last problem is again in put in the same problem, but put in a different context, where we have given with a air conditioning plant of rated capacity. So, Q rated capacity for the plant is 40 tons of refrigerant. But what happens is that a test on heat rejection to the atmosphere showed the following reading. That means, there is a plant, and some test was done based on the calculation how much heat got rejected to the atmosphere, and the heat rejection was done by a cooling water which is used in the condenser, that for which the inlet temperature was 30 degree centigrade and exit temperature of this cooling water was 40 degree centigrade. That means, refrigerant rejected heat to the cooling water, and mass of the water flow is 4 liter per second. Now, from this we can calculate the condenser load, and say also we are given with the power input to the motor, that is 46 kilowatt with 96% efficiency. That means, the motor is 96% efficient with its rated power 46 kilowatt. So, we know the compressor load or power input load. So, first thing that we need to calculate, what is condenser load, and this is evaporator or rated load of evaporator or the plant. So, first thing you have to calculate condenser load. So, we say Q dot C is nothing but m dot water specific heat of water into temperature difference T out minus T in. Now, m dot is 4 liters per water, C dot is specific heat of water, that is 4.18 kilojoule per kg Kelvin, and T out minus T in, that is 40 minus 30. So, when you multiply this, the number what we are going to get is 167.2 kilowatt. So, condenser load we got 167.2 kilowatt. Compressor load, so we can say W dot in, and it is given as 46 kilowatt into its efficiency 0.96. So, this number is 44.16 kilowatt. So, from this we can actually calculate what is evaporated load, that is 167.2 QC minus W in, because if you look at this particular cycle, W in, it is Q C, it is Q R, and this is air conditioning plant. So, T low temperature and T high temperatures. So, QH, QC, QR is nothing but QC minus W. So, 167.2 minus 44.16. So, Q dot R, that is the actual refrigeration load, becomes now 123.3 kilowatt. Now, if you make it to ton, then 123 divided by 3.52. So, this is about 35 ton of refrigerant. So, actual rated load is 40 TR. So, so we can say that plant is operating below its rated capacity. So, it is a feasible option. Okay. With this, I conclude this talk or class for today. Thank you for your attention.